Let's talk about the pH scale and the significance of the numbers that are in it. The first thing I want to remind us is that this H right here, it's really referring to the hydrogen ion concentrations that all acids have. Like solutions have hydrogen ions and they can be counted, and then that can be represented in this scale that is going to have a center of 7, right? And that center we're going to call neutral. So if we have any substance that has a pH of 7, we're going to say it's neither an acid or a base, but we're going to say that it is neutral. And any number above that 7, so 8, 9, 10, and the scale goes all the way to 14, we're going to describe those pHs as basic or alkaline. And any number that's going to be below that 7, so anything lower, we're going to call those numbers acidic, or describing substances that are acidic. All right, so what's new now is what is the significance of every jump in pH? Okay, so let's compare a few substances. If I have a substance that has a pH of 7 and I want to compare it with a substance that has a pH of 6, I would say that the substance with a pH of 6 is 10 times more acidic than the one that is 7. 6 is more acidic because it's lower, and 10 times because that is the representation of a jump of one value in pH. It is not just 1 time more acidic, it's actually 10 times more acidic. Let's see another example. If I'm going to compare a pH of 5 with a pH of 3, so I'm going to go 1, 2 jumps, right? And if every jump is truly 10 times more acidic, right? Not just twice more acidic, but 10 times 10. 10 times 10, it's actually 100 times, right? 10 times 10, 2 zeros now. So a jump on 2 pHs going down to the acidic side is going to make a substance 100 times more acidic. We could also think about this the other way. If I say, well, what if I'm comparing a substance but going up the scale? So I'm going to compare a substance 8 with one that is 11. Ooh, okay. So now I'm saying, well, this is a jump of 3 units, right? 1, 2, and 3. And that would be, if each one of them is representing a jump of 10 times 10 times 10, that is 10 times 10 times 10, that is 3 zeros. So basically this is a thousand times, right? But then if I'm thinking about it going up the scale is going to be more basic, right? I'm going higher on the numbers. That means that this is going to be 1,000 times less acidic, right? 1,000 times less acidic, as opposed to the other examples that we have, in which case a 6 is 10 times more acidic, more. And this was 100 times more acidic. A 3 is 100 times more acidic than a pH of 5. So you're getting the hang of it. You need to look at two things. You need to look at the direction that you're comparing. Are you going to the lower numbers or are you going to the higher numbers? And you also need to look at whether you are making a change of 1 unit or 2 units or 3 units, and making sure that each unit is representing a change of a times 10 in scale. So let's write some of those things down. First, that if we go to lower pH numbers, that means more acidic. The lower the number, the more acidic. If we go to the high pH numbers, we are thinking that is less acidic. We're going away from those low numbers, less acidic. Then now the significance of each number. So 1 pH unit really means a 10 times change either it's going up or down, so less acidic or more acidic. 2 pH unit change, it's actually 100 times the 2 zeros for the 2. Similarly, 3, and you could continue on and on, 3 units of change would actually be 1,000. Really easy to tell because of the 3 zeros. That's how you would do it. You would decide you're going up or down, more or less acidic, and depending on the amount of jumps that you're making on the units, you are thinking that is 10, 100, 1,000, 10,000, depending on the zeros. Those are the jumps that you make on the scale. Okay, great.